Hello, everyone, and good afternoon. My name is Laurent. For those of you who doesn't know me, the communication coordinator of TwinEU project, and this is the second episode of TwinEU Shorts, this webinar series that we created to put the spotlight on the achievements and the results that were so far produced in the 8 demos of the project. So today the topic is the Dutch and French demo. So for this, we have our colleagues here from TU Delft, May Biatwe, and also Lucas Salugian from RTE. And we will start with the Dutch part. So May, I will just give you the floor without further ado.
Thank you for your introduction. I'll share my screen. Can you see the screen?
Yes, it's perfect.
Yes. Okay. Yes. Good afternoon, everyone. As Laurent introduced, today we'll be presenting about the digital twin, the progress of what we have developed so far in the Dutch pilot. My name is Mimiatwe. I am a PhD candidate from Delft University of Technology. And so in our Dutch digital twin, so our partners include from transmission system operator, distribution system operator like Canon Studying, ADN or Jetlex, and then TUDEF is the pilot leader. So mainly in the Dutch digital twin, we are developing the cybersecurity and the stability use cases. So based on the digital twin testbed that we built. So before we start, why do we need digital twin? So modern power systems, they are becoming like cyber physical power systems that are highly interconnected with electrical infrastructure, communication networks, and control systems. So consequently, if there is disturbance or cyber threats, so they can propagate across the system operators or the regions and across borders. And another limitation is like if we have multiple system operators, but they have a limited system-wide visibility, and there are a lot of data silos and fragmented data across the operators. And if we want to test the cyber attacks, MedDex, or the other types of simulation, is also risky and costly to test in the live operation. So to address these challenges in this pilot, we are developing the digital twin of the Dutch transmission and distribution system to provide a safe environment and to perform different analyses such as monitoring or the cyber threat detection and perform simulation analysis and assess the impact of the cyber attacks and provide the decision support. So that's the idea behind why we are developing the digital twin. So our digital twin framework integrates transmission and distribution networks. When we talk about the digital twin, we need to have a real physical system. So we are modeling that transmission and distribution networks to present as a physical power system representation. And we have the communication layers connected through the SCADA, through the digital twin framework. So where we perform different types of simulation and run what is scenarios. And then we simulate in the control environment. We simulate different types of attacks and detect the attacks and assess the impact and cascading failures. And finally, identify the point of no return and provide the decision support. So the framework, this can be kind of a realistic cyber physical test bed for the future grid studies. So based on this, we achieved some results by May 29. So as I mentioned, we are focusing two use cases. One is for the cybersecurity. So in the cybersecurity part, we have developed the integrated Dutch digital twin that combine the transmission and distribution networks and physical and communication layers. We perform different cyber attack simulations and collect the data so we can train the AI models for the cyber attack detection. So we monitor the communication network and then we develop the AI-based attack detection methods using federated machine learning. And we also develop methods to assess the impact and then to quantify the system impact and identify the point of no return. So this is for the digital twin testbed itself. So based on the results and the progress, we have published one journal paper, two conference papers, and we are also working on another journal and conference papers at the moment. As I mentioned, so we are focusing on the transmission and distribution model. So I will give you a brief information about that. So we built a dynamic model with various protection schemes, and then this model is connected to the communication layer through the OPC server. So we exchange some parameters and between the physical system and the digital twins, so we can perform different analysis. And this is regarding the method of the attack detection. Because of the limitation of existing centralized machine learning approaches, we developed the federated learning approach, which can offer the privacy, like privacy preserving method. This is also the framework from one of our conference papers. So basically, to come up with the attack detection method, we generate the normal and anomalous network traffic that we simulated, and we're using our platform. Using our testbed, we cover different attacks such as malware, exploits, DOS attacks, and network scanning, covering different OT protocols. We also received the preliminary results, and because of there are some challenges in different scenarios, so we are developing and expanding the current method to solve the federated learning issues. We also performed the impact analysis, so to verify the cascades of the model. So we replicated the Italian physical blackout scenario on the Dutch transmission network. So we create the fault, and then we analyze how this kind of event leads to cascade events. So we also simulated the cyber attack event similarly. So to analyze the impact of a cyber attack and how it will be different from physical impact and the cyber attack impact. So in this case, we can see for example, the analysis is like we can see this kind of cyber attack can result in the loss of load of the nearly half the load of the entire grid. So we ran other similar scenarios as well in our pilot. This is regarding how we are using the digital twin to perform different simulation analysis. And regarding the stability part, so we developed a reduced equivalent model of Dutch EH3 system for system level analysis. We also performed real-time dynamic simulations to analyze the critical system behaviors. And after that, we established stability KPIs based on the voltage and frequency performance. And finally, evaluated representative future operating scenarios to support stability-oriented digital twin applications for low inertial grids. So what kind of takeaway we can have based on the progress that we have, and so the first one is we can say that isolated analysis is not sufficient because the power systems are strongly interconnected, and the real world testing is very limited and risky. And then that one is the static offline analysis cannot fully capture the fast system dynamics. And then that one is, as I mentioned, there are a lot of data silos across the system operators that can limit the coordinated cyber attack detection and analysis. So we come up with the privacy preserving method to show the potential of how we can do a coordinated attack detection without sharing the sensitive data. And also, most importantly, detection alone is not sufficient. So we need to understand how different cyber attacks and then have impact on the system so that we can also come up with informed decision making. So to sum up, so digital twin basically can enable us to for the proactive, resilient, and secure power system instead of the reactive control. So that's comes to the end of my presentation, and I'll be happy to answer any questions.
Thank you very much, May. One can see that your demo is really in a mature stage. Maybe if you allow me to have just a short question. So there is still a little bit more than half a year left from TwinU. Do you have still any kind of validation or testing phase left in this demo, or is more the evaluation part from now on?
So yeah, we still need to do more experiments because so far, so before half of the project, we did analysis for the transmission system, and we built the transmission network model. But right now we have integrated both transmission and distribution. So for that integrated model, we will do more analysis. And also regarding the attack detection, we are expanding and improving our method.
Okay, I see. Yeah, I would suggest that if there is any question maybe from the audience, we can give it 1 or 2 minutes. So if there is a question, you can raise your hand and I can enable your microphone. But if this is not the case, then we can move on to the French demo. And Luca and Olivier, the floor is yours.
Okay, can you hear me?
Yes, and we see the screen as well.
Okay, thank you. So good morning, everyone. So we will present the French pilot with Oliver. So Oliver and I are working at the R&D department of RT for more than 20 years. And so here the topic is focusing on a digital twin to train operators on future complex situations. So the situation that involve obviously the physical layer, so the grid, the electrical grid, but also the cyber layer, meaning that we model the telecommunication grid and the SCADA system that are upon this electrical network. So this work is a collaboration between RTE, CRECIM, Aachen University, Fraunhofer, and TU Delft. CRECIM acts as coordinator of the pilot and between the different partners. So next slide. Okay, so this slide just to remind the different objectives and challenges of this pilot. So what we want to develop is a kind of twin of the control room that can be used to train the operator, as I said before. But we want also to test new decision support assistant that we are developing typically in our R&D department. So meaning we are developing some new assistant based on AI, obviously, based on robust optimization to tackle uncertainties, etc., and to decrease the complexity of all this, and to help operators to still take a good decision close to real time. And this is also very, very much related to what we call now trustworthy AI, for example, how to test the robustness and the reliability of the different assistants that we are developing based on AI with some scenarios and some scenario to just validate those new models. So this is very important regarding also this topic. So this twin, we also can imagine to replay some real life scenario that have resulted in collapses. It's not so often, but we can replay those scenarios because we can take these scenarios coming from the real SCADA and we can replay them before the collapse. And even we can imagine to prepare also some scenarios with our DSO and typically NADs in France when we can anticipate a little bit, for example, very tense winter like the one we had in 2022. And this could be very good to have this kind of twin to make some co-simulation with the DSOs. So what we have also to keep in mind is that we want to model cyber physical aspects, so meaning that we want to deal with also new automatic controller. We have some closed loop controller using some MPC approach, etc. So we want also to model this and to simulate this. We want to model the telecom network, as I said, and of course, we want to all this to be scenariized, to be able to simulate events on both the physical, as usual, with outages, etc., but also with some telecommunication events, delays, loss of observability, etc. So the other point that is very important in this twin is that we want to set up this twin to work on at least the French network. So that means more than 6,000 electrical nodes and more than 13,000 of lines and transformers. And so we want to perform this co-simulation on very large network and not only on IEEE network for validation purpose. So that's it. So next slide, I think it's Oliver that will present the global architecture.
So let's focus a bit on the architecture of our twin. On the left side, in gray, you can see the trainer UI. On this side, we have the game master system, which Lucas told a bit of. The game master is responsible of playing for example, scenarized events, which can be expressed in the form of domain-specific language or DSL. The UI for the trainer is a SCADA-like UI, but the trainer is authorized to do actions that are not available for a trainee. For example, he can act on generation or loads, and the trainee can't do that. On this module, the Game Master system, we have also components to compute key performance index of the simulation. If we look at the right side with the black screen, we have the trainee UI, which is a SCADA-like interface. On this part, the information received is measurements, events, and the trainee can also send commands and set points to the system. You can also see at the bottom that with the same kind of information, measurement, signals, we can connect automata or external software assistant, which can be, as I said, connected with a SCADA-like interface. At the top of this schema, you can see the simulation brick, which is made of the grid simulator based on Dynamo, which is an open source simulator, the dynamic simulator. it will simulate the grid. The grid. On the second component is what we have called the information flow model. This part is responsible of simulating the communication aspect, and for that it uses topological description of the communication network. And the last component is the asset simulator, which is responsible of simulating everything that is not simulated by the other items. So, for example, when somebody goes into a substation to do some maintenance, his first action will be to indicate that he is in the substation. This kind of information is not relevant for a grid simulator, but it is relevant for a dispatcher, because some maneuvers are forbidden when somebody is in the substation. So this kind of information has to be provided to the trainees. And this is the role of the asset simulator to simulate this kind of information. On the bottom, you can see the logging system, and also, as I said, the key performance index indicators components. At the center, we have the orchestrator, which is responsible of orchestrating all the components of the system. And that's it.
Okay. Did you mention the smart assistant layer?
Yes.
Yes. Okay. Sorry. Okay. So last slide before the demo. Voilà. Okay. So description of the area that we will see in the demo. So it's a small area with a substation with 3 transformers. The trainer will operate to open 2 of them, so we can imagine, for example, a planned outage on the first transformer and a fault on the second one, if we want to be in real life. And so this will lead to some constraint on the area, on the third transformer, obviously. And so the operators will have to operate, and what we will see in this very brief demonstration is that the operator will take some topological remedial action, and also we will show how we can also manage to call, for example, the generation unit to lower the generation, because we have 4 generations that are very close to the congestion in this area. So that's it, and we will also simulate a loss of observability, and we'll see the impact for the operator. So we recorded a video because we want to avoid the demo effect, obviously, and we want to keep the time to less than 15 minutes. So I hope we will succeed in this also. Alors, so the demo, I have to switch from, okay, talk, and I think I have the video here. So I start. Okay, so to start the session, you must be logged in a lobby, the video game. So you can create a session, so meaning a set of files, so the power grid case, dynamic data, and the scenario you want to play to create. So that's what we are doing here. Then you decide to enter one of the active sessions. In this case, we want to play as a game master. So the game master decided to start. So play, I don't know if we can see, but at the top you have a button to run the simulation, to start the simulation. It took some time because we have to upload all the components of the game. He will display a view of the substation of interest, also different graphs showing the status of certain variables of the network. So especially here in this case, the components. I will make just a brief break. So here the current on the different transformer that we are looking at. So the game master has access also to all the system variables. So this is very important because he has the release state of the grid at each second. Every second, he has the complete state of the grid. It's not the case for the operator that is based on the SCADA. So we can see also as the demonstration has started, we can see at the bottom some constraints. Okay, it's some voltage constraint. We don't care in this demonstration, but I hope our operators cares about. So now the trainer will play a little bit with the breakers. As I said, he will switch off one transformer. So we can see on the curves that there is a drop. He will play on this second breaker also for the second transformer. Okay. And what we have here is that we have a congestion, an overload of 20 minutes. It's okay. I will be just 10 seconds back. Okay, so here after the opening, we have another overload of 20 minutes on the third transformer that we can see. So now we will switch towards the trainee. Okay, so it's another screen. So we don't want to make the two screens in parallel, but it's in parallel. Okay, obviously. So, okay, what we can see from the SCADA side, so it's couples.
Okay.
Voilà. Okay.
So this is the trainee side and the SCADA view. You can see on the top feeders that we have more information than on the trainer side because we have added values which are measurements. So the first values on the top feeders are active and reactive power, but those are estimated values. And next, you have prefixed with an M. We have the active power and the reactive power, which are measured
every 10 seconds.
Every 10 seconds, about 10 seconds. If you look at the right side on the curves, you can see the measurements. For example, it's active power on the transformers, and you can see a little circle which indicates that we have received a new value for this measurement. At the bottom, you can also see the logbook, which is generated by the Dynamo simulator, and you can also see the constraints that are active on the system. Now we have 4 constraints for low voltage constraints on the system. This view is before opening the 2 transformers, but let's play and we see the effect.
Okay, so the trainer opened, as we see before.
Yeah. The trainer has opened the two transformers, and we can see on the right side on the curves that the flow on some transformers is equal to 0, which is normal, and we can see on the green curve that the flow on the third transformer is has increased because we are on the on the opposite side, the value is negative, but the flow really increases.
In absolute value, it's increasing.
It's increasing, yes.
And there is a constraint.
And on the lower side, we have also displayed the frequency, but the frequency is not available for the training, and that's why we don't see it.
Sorry, yes, I will. Okay, so we have the. Sorry, because I was with the conclusion of the.
Yes.
Okay, so here we have the.
Two transformers are open, so we have an overload on the third transformer, which is displayed on the constraint part.
Okay, and so now.
Okay, so here the trainee has played his remedial action, which is opening the bus bar coupler of the voltage level. We can see that now we have two nodes on the substation. We can see the voltage and the phase only on one node because we haven't the state estimation hasn't been done since the opening of the bus bar coupler. And we can also see that on the green curve, that the flow is a bit lower and it's sufficient to eliminate the overload. So we can see on the dynamo constraint part that the permanent limit overload has disappeared. It's indeed.
Okay, and so and so we get back to the trainer and we reclose the coupler that was opened by the trainee to make another scenario. Okay, the constraint has disappeared, and now we have as we close the coupler again, the constraint reappears obviously. And
we are late.
And yes, we are late, but okay. So we will see also from the operator's side. Okay, the coupler was reclosed.
Mm-hmm.
So also in the
trainee side,
in the trainee screens, you have the closing. Yes.
Mm.
So what we will do back to the trainer side. Now we are going to dynamically simulate a loss of observability on the telecommunication grid. And to do this, we will use a file written in DSL. So the DSL here is the language that mentioned Oliver. You can generate all the events we want on the grid, electrical grid or telecommunication grid. In this case, I will just copy paste the two lines to lose observability on the substation that we are focusing on. The name is MQES.
Right.
IS. So if I do this, okay, I take those two lines and okay, I will put it in the DSL terminal. The command has been executed. So we are changing and we are putting some drop on the observability, and we are.
So it doesn't affect the game master, the trainer view, but it will affect the trainee view because
yes. So what we are doing here, the trainer will modify, for example, the breakers of the two transformers again, okay? So switching on the two transformer breakers, and also he will play with the coupler of the substation, and we'll see what happens on the okay, it's the video, so we have some lag. Okay, so this is the real state, but as we lose observability, what we have on
the trainee side, we don't see anything, but we can eventually see some changes in the grid state if we do a state estimation, because we haven't lost all information on the grid. We have only lost information on the substation. So perhaps the other information and the state estimation will help us to see what happens. But for the state of the grid, the measurement doesn't change. The state of the switches doesn't change until we recover the observability.
Okay, so that was an event on the telecommunication grid, and we can see that there is effects, obviously. So we are coming back to the trainer, and now we will recover the observability of the grid. Okay, so with okay, so we are processing. Okay, up, and then we'll re-put the system under constraint by replaying the transformers and the coupler, and we will try to use another. Okay, so we'll see that there is the constraint again. Okay, we will try to have another remedial action by playing not on the topology and having the operators in the loop, but we will mimic the fact that the operators will call some power plant or power unit and to lower the generation. So obviously it's not the operator from RT that will play the lowering of the generation, but the game master who will play this role of a producer. And so now, if we look at the 4th generation that I already mentioned in the introduction slides, we have Blayet, that are 4 big units in France, and we will create a function here in DSL. We can generate some function to. Okay, so we did a lot of things during the video, the recording, but so okay. So here with the DSL, we will create a function that will lower, using some ramps of 10 seconds, that will lower the production of a unit that we will mention in parameters. So the function here is, okay, so it's from now plus 5 seconds at now for plus 15 seconds. What we want to do is to set up the set point.
To lower the set point.
And here we will lower the set point, but this one will set the target of the generator. So it's a very generic language. So we instantiate this function, and then we will use this function to lower the different Blayet, the different generation units. So we'll use this function that we set up. So, and we will put the name of the generator and the amount of megawatts that we want to set up to this generator. So the function is a kind of shortcut, and we will instantiate it. And so we will see the ramp of this 1st generation. Okay, so we can see that it starts to decrease. So we have.
It's small, but you can also see it on the substation view values.
And so now, okay, and as you can see, it's not sufficient because we still have some overload. So we'll do the same for the other generator and for 2 others Blayet. And normally, the constraint will be relieved. Okay, this is the end of the constraint. This is the end of the demo regarding the business aspect. I have 10 seconds more showing you that we can open many things. Okay, so we can, for example, you can display the frequency. You can also display, this is the telecommunication grid. Okay, so don't take a photo because this is the real French topology grid in a way.
Communication, right.
Communication grid. So with all the RTU and concentrators, and we can modify the characteristics of the delay, the drop, etc., etc. For a link. For a link. Yeah. And I think we have a voilà. Okay, so that was the end of the video. I also wanted to mention Ology company that works with us in RTE. Within RTE, it's not in the consortium. I already mentioned all the partners, but Ology is deeply involved also with us in this TwinEU project, but in the RTE department. So thanks to them also, we could achieve not only this demo, but the development of all the modules. So, and this is the end for me. So I have last slide. Okay. Thank you. If you have any question for Oliver or I, for me, sorry.
Thank you very much, Luca and Olivier, for this demo. We are running very, very late, so if there is, maybe one question, then of course we can find some time. So please just raise your hand if this is the case. In the meanwhile, I can tell you that all of the slides and also the video will be shared on the TwinEU channel, so you can take a look afterwards, of course. And also I have another public announcement is that the next episode of TwinEU Shorts will come already next week with the Slovenian demo, and then we will have another session before the summer break with the German demonstrator. So you can already register on the TwinEU website, but also it is going to be shared on the LinkedIn and the other channels as well. So I don't see any raised hands in the meanwhile. So I would like to thank you for all the presenters, May, Luca, and Olivier, for this, and all the participants and the audience to join us today. And yeah, hopefully we'll see you next time, and we wish you a nice rest of your day. Bye-bye.
See you. Bye.
Thank you.